What is going on? It is Sunday, May 22nd, 10:36 a.m., 2022. And yeah, I am back after another week of crazy stuff going on and me not able to produce that video every day that I promised. Okay, so fool me once, shame on me. Fool me twice, as George Bush famously quoted, last George Bush, you can't get fooled again. Okay, so anyway, I'm not going to try to fool anybody. I'm going to do my best to get you a video every day like I promised. And yeah, I want to be consistent with that, so let's get it started. This is Coding with Shaft the Algo Man. I have an ongoing debate about what the name of this channel should be, whatever the case is. I'm gonna call it Shaft the Algo Man. There you go. Or Algo Guy, whatever's friendly, or Shaft the Algo Guy. All right, there you go. And yeah, so if you like my videos, like, subscribe, comment, and do all that good stuff that lets the algorithm, right, know that I'm doing well. Okay, thank you. All right. Let's get to it. The problem is 852 peak index in a mountain array. And so this is a classic problem. And this is actually, I think in CS classes, if I remember mine, and others that I've seen lectures, one of those MIT lectures, I think, that are pretty popular by that Eric Demain guy from who's a professor there, was a super young professor there. This peak index in a mountain array is a fundamental problem, and they teach it in basic while they're teaching you searching mechanisms, array searching mechanisms. So you got to understand this kind of thing. And I mean, yeah, you have to. I think this is one of those problems they tell you in coding interview prep stuff, not to like memorize things, but this is one of those problems that's really good to just fundamentally understand and have a good grasp of how to solve like that, because then a lot of problems follow what's called the alternative binary search template. And not just kind of giving it away, that's kind of the solution that's optimal for this problem, right? So because you can do this two ways. You can do this using a linear search, or you can do this using a binary search. And the expected optimal way to do this is using a binary search. So, but let's just first go through the statement, and then we can get to the actual solution. So let's call an array AR a mountain if the following properties hold: AR.length is greater than equal to 3. There exists some I with 0 less than I, AR.length minus 1, such that AR of 0 is less than AR of 1, such that AR of all the way up to AR of I. And then when you hit that AR of I is greater than AR of I plus 1 is greater than so on and so forth, all the way to AR of AR.length minus 1. And so basically what this is saying is that there's some index I such that every element before it is going up and every element after it is going down. So it says, given such an integer array R that is guaranteed in bolding to be a mountain, return such any I such that AR is less than AR, so on and so forth. So the conditions above here are held. AR of 0 is less than AR of 1, is less than AR of I minus 1, and is greater than AR of I plus 1, and so on and so forth, right? So I is the center of this array here, or not the center, it is the peak in the array. Okay, so and there should be one peak, right? Either way, so like here's an example of that array: 1, 2, 4, 6, 99, 101, 50, 32, 11, 2. Let's call it 2. Okay, you see this? So basically up to here, this is increasing steadily until you hit 101. And then afterwards, 64, 32, 11, 2, this is decreasing steadily after you hit, after you pass 101, right? So then that's how you know 101 is the peak, okay? And, there's no indication of whether this is a sharp peak or a not so sharp peak. It doesn't matter. It's just saying that we're looking for the peak here. Okay, and now the easiest way to solve this, right, is pretty much, I'm just going to show you the slow way, right? first. Slow. So you got I is less than I, AR, length, I plus plus, if AR of I is greater than AR of I minus 1, and let's just start it at 1, because and we can just return -1, and then and AR of I greater than AR of I plus 1, return I. Okay, so this would in theory work. Let's see. Right, so basically you put in, this is just saying, this is literally, a linear test case. And this might not even hit the, yep, that worked, right? Okay, and it was fast enough according to Leetcode, but it's really not the fastest solution here in the grander scheme of things. Okay, Leetcode should probably change some of their test cases that really indicate this, but let's go and try to do this the smart way, so to speak, right? Okay, so, and this is, by the way, in interviews, this is what they expect, this way. So we're going to do binary search. So I'm assuming that you have an understanding of how iterative binary search works. If not, there's plenty of videos out there, and I may link a few myself. But I'm not going to go super into the basic idea of how binary search works, because it's something that you should have at the tip of your fingers. Either way, okay. So, but this just a quick refresher. In binary search, you have a you start off with your boundaries in your array, in your search space, right? So your boundaries are where you start. In this case, we're starting at the beginning of the array and where we end. So that would be the end of the array. And so while start is less than end, right? Remember, we keep kind of the actual original binary search is similar. While the start is less than the end, you calculate the midpoint and you determine iteratively over and over again. You readjust what the start and the end of the array is, and readjust the midpoint based on the start and the end of the array until you find your target. Okay, so that's why you have this while loop here, while start is less than end, right? And the midpoint in this case, we're going to calculate it the same way as we normally calculate midpoints in binary search. Okay, so this is start plus start end minus start divided by 2, and that's just you could also do start plus n divided by 2, but then you would have long integer overflow, and this is a common optimization to prevent that from occurring. Okay, so not to get into that too deeply, but because I feel that if you're watching this video, you've probably seen that before. Okay, so while start is less than n, now here's the part that I think bears requiring all explanation. Okay, now remember, AR of mid, so we got the midpoint. We're starting at the midpoint. We're gonna keep correcting our position until we find something that holds our binary search condition to be true. Okay, so first, remember, if AR of mid is greater than AR of mid plus 1, that means if we're in a part of the array that's descending monotonically, right? Because that's what the mountains do essentially, or at least just decreasing, then we want to be in the left half of the array, because if we go back to our example, or even put a new example, 7, 5, 3, 4, okay. If we go up to here, right? AR of mid, like we start off the midpoint of the array, in this case, like literally somewhere here. Okay, we start there, but let's actually do a better example. 9, 10, 11, 12, 13. Okay. So let's say we are at the midpoint of the array, and that midpoint would be, initially it would be here, okay? So what's going on here? If AR of mid is greater than AR of mid plus 1, that's not true. So let's start with the end condition. If AR of mid is less than AR of mid plus 1, then we end equals mid. So this means that we're going to shift the end from here, from 1, in this case, if this is the midpoint, all the way to AR of mid. Sorry, we start here. Start. And we start at AR of mid plus 1 because we're here and we see that the midpoint, let's say the midpoint 10, is less than the next element 11, and so there's no point in looking before the end of this array because we know that the midpoint, there's no way to satisfy the peaking condition before while in the descending part of the array because every element will be descending. So we must actually go to the right side of the array because the peak's got to be here somewhere. All right, so what we do is we just do that. We just get it out of the array. Okay, we by setting the starting to here, where the previous mid was, and the next element, because we don't care about mid anymore, because that's already proven to not work out for us. Now, what if it's the other way around? What if, and I'm gonna write this condition out. If AR of mid is greater than AR of mid plus 1, right? Then we just have to send end equals mid, okay? By the way, I'm gonna just return okay, -1. Okay, so if AR of mid is greater than AR of mid plus 1, that means if we are in the descending part of the array, right, like if we get to the point here that we're here, right, because this is, then we don't care about this, so we just set the end to mid and not mid plus 1 because mid plus 1 is already the next element, and so we don't care about that. Now, is this enough? Let's see. I'll tell you right now, that this is not enough because we're not actually finding the peak. So how do we find the peak here? Okay, finding the peak is pretty straightforward at this point because all we need to do, okay, we can look at, so where is the peak? The peak is in a situation where we have both AR of mid is less than AR of mid plus 1, and AR of mid is greater than AR of mid plus 1, and AR of mid is greater than AR of mid minus 1, because, right, so here's the peak, this is AR of mid plus 1, this is AR of mid minus 1, and that's the only time in this entire array that we have a situation where there can be a peak at mid. Okay, that's what we have to understand. So so in this end condition, if we get to a situation of AR of mid is greater than AR of mid plus 1, we will also have a situation at some point where AR of mid is greater than AR of mid minus 1, and then we return mid. Okay? Now, that looks weird, right? But let me assure you, it's expected that you know that. Let's try it. Okay? And solution. Okay, great. Now, ignore the memory for a second, and just note that, again, these test cases should be adjusted, but this is going to be unequivocally, generally speaking, it's just going to be overall, as n goes to infinity, a much faster algorithm because it's doing the work in O of log n time. Okay, where the previous operation was O of n. So we don't want an O of n we would prefer a faster algorithm, and so that's why this is faster. Okay, so if you like this video, that's it. Like, subscribe, and comment, and let me know how I'm doing. And thanks for watching. I will see you later. Have a good Sunday.